All right, how's it going, class? Welcome back from the long weekend. I hope you enjoyed your time off. Uh, so, today we're going to be jumping right back into dynamics, right? Okay. And now today I'm basically going to go over two problems, and they both look identical, almost. All right. It's going to be a ramp with a box on it, all right? Well, oh, Lord. Okay. It's going to be a ramp with a box on it. First, we're going to have no friction. And then the second time we will have friction, right? I'm going to work through this example. All right. You guys basically already know how to do problems like these. You do the sigma fx, sigma fy, the free body diagram, all that kind of neat stuff, and you should be able to solve it just fine. But now that we have a ramp, we have an angle here, theta. And it's time that I teach you guys why we use cosine and sine, right? So if we have a triangle, right? Let me just draw this triangle here. And we have the angle, right? We have what we know from the Pythagorean theorem called the hypotenuse. The hypotenuse. We also have the leg called the adjacent, right? And this leg is called the opposite. Now, why are they called adjacent and opposite? Well, it's called adjacent because the angle, as you can see the angle right here, this angle is adjacent or directly next to it. Sorry, there's a knocking noise. Let's check on that. Never mind, it stopped. They must be doing construction outside my house. Okay, so that's totally my bad. I didn't anticipate that. Let me go over this again. So we have the angle right here. The side that is connected to that angle is called the adjacent side. And you might be able to tell that there's two sides connected. Well, the longest side is the hypotenuse. So that can't be adjacent, right? That's why we have adjacent and hypotenuse. Now the opposite is just the angle that doesn't touch the side that doesn't touch the angle. So let me write that down. Hypotenuse is just the longest. Adjacent touches the angle. And opposite does not touch the angle. So we have that. Now, why we use sine, cosine, and tangent? Well, we haven't used tangent yet, but the reason why we use sine and cosine is because sine is equal to sine of an angle. So I'm going to write theta here, right? You've learned theta. It just means any angle. Sine of theta equals the opposite divided by the hypotenuse. Well, let me write it all out. Opposite divided by hypotenuse. Cosine of theta is equal to adjacent divided by hypotenuse. And there's a third one called tangent, and that's equal to opposite over adjacent. Now, how would you possibly memorize this? Well, the easy way is to look at the first letter, SOHCAHTOA. So a lot of people just say SOHCAHTOA to memorize it. So you know that sine is equal to opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, right? The reason why we can solve something, right, is if let's say we had a vector. Let's say we had a vector at an angle of, I don't know, 37 degrees, right? I love that number. And 20 meters per second. We know that we can have we can break that down into x and y. The x and y. Well, when we solve for the x, it's equal to 20 meters per second cosine of 37, right? Well, 20 meters per second, this leg is the hypotenuse, right? All right, and then if we have cosine of theta equals adjacent over hypotenuse, if we just multiply both sides by hypotenuse, right, that becomes h cosine of theta equals a. Now, a is the adjacent angle, or the adjacent side. The adjacent side of this triangle is x. So when we do the hypotenuse times the cosine of the angle, we're just finding the side that's connected. Does that make sense? Okay. So this is something called a horizontal angle. All right. I'm going to give you multiple ways to approach these. If it's a horizontal angle, that means that the adjacent side is horizontal. So that means that cosine solves for x and sine solves for y. Okay? Now, let's say we have this ramp. All right? Now that we know something about cosine and sine at least, we're going to tackle the ramp problem. Ramp problem. Okay. Let's say we have a box on a ramp, and this box has mass m. M equals 24 kilograms. All right. Now, let's say that this box is on an angle of theta, the ramp of angle theta. And let's say theta is equal to 53 degrees. I would like for you guys to find what is the force exerted on the box down the ramp, right? So what's the first step? Well, we need to find our x and y components. Now notice this. Should we do this as our x and y, or this as our x and y? Now if you think about it, the answer is this one. We should have this as our x and y components, right? Because to the object, the side-to-side movement would be tilted because it's on the ramp. So we want to use this is the x-axis, and this is the y-axis. Okay? So let's say this is x positive and this is y positive. Now, let's draw a free body diagram for this thing. This is mass m. Well, we have the force of gravity acting down. That will not change. Just because it's on a ramp, force of gravity goes down still. And then the other force on it is normal force. Now, normal force does not go straight up. In fact, if you remember the definition of normal force, it goes perpendicular to the surface. The surface here is this ramp. So perpendicular to it, or in other words, 90 degrees to it, would be this angle. Right? Now, the ramp is at a 53-degree angle, right? So we will use that information soon. Now let's do our next step, which is to find sigma fx and sigma fy. But uh-oh, look at this. The f of n aligns perfectly with the y, but fg is now diagonal. Well, it turns out we can break the fg into two components, fgy and fgx. All right? Now, why do we do that? Is because the x and y axes we chose are diagonal. Fg is pointing straight down. So we have to conform Fg into the correct, into the correct angles. So it actually turns out, right, by geometry, you guys are not expected to have taken geometry yet, so let me just tell you that if this angle is 53, then this angle is also 53. Okay? Just need to believe me on this one. So that means that FGY, right, is going to be the adjacent side. So FGY is equal to FG cosine theta, and FGX is equal to FG sine theta. Now this is the reverse of what you learned previously. That is because this is called a vertical angle. The angle is against the y-axis. So for a vertical angle, x is solved with sine, and y is solved with cosine. Now, let's keep moving forward. What are all the forces that we have in the x direction? Well, if we remember the x direction, it's side to side, but in this case, it's diagonalish, right? So the only force in the x direction is this one right here, FGX, all right? What about the forces in the y direction? The forces in the y direction, there's two. There's f of n and fgy. So it's f of n minus fgy. And that equals 0. Why? Because remember, the box is not flying out of the ramp. It's not accelerating above the ramp, and it's not sinking into the ramp. So it doesn't have a y acceleration. Whereas the x does, right? Now we know, well, what did we initially want to find? We wanted to find the force exerted on the box down the ramp. Well, down the ramp is this direction, right? What is the only x-axis force we have? Well, it's FGX. So, force on the box down ramp, or down the ramp, is equal to FGX, which is equal to mass times acceleration. Okay? And now we know that the acceleration is equal to the, the gravity. Whereas FGX, right? We know that FGX is equal to FG sine theta. So we have FG sine theta equals sigma Fx. All right? Now this may have confused you a little, so I'm just going to rewrite it. Sigma Fx equals FGX. All right? And we just substituted the FGX here for the FG sine theta that we solved here. So Fg, the force of gravity, is equal to the mass times the gravity of something, right? So that means that we have mg sine 53, because we have a 53-degree angle. The problem told us that. And that is equal to the sum of the Fx forces. What is the mass of the block? Let me look back up here. It's 24 kilograms. So push this up a little. So we have 24 kilograms times 10 meters per second squared times sine of 53. And sine of 53 just happens to be 0.8. Right? And that is equal to 240 times 0.8. Let me get out my phone so that I don't leave you guys hanging on that one. It is 192 newtons. All right. Now, does that make sense? Well, that's how much force that gravity is exerting on it in the x-axis. Now, normally, the force of gravity would be mg equals 240 newtons, right? But now remember that the box being pulled down a ramp makes the gravitational force in the x direction less, right? It doesn't fall at the same speed as it would if you just drop something. If you drop something and you just push something down a ramp, they don't fall at the same speed, right? That's the reason why. Right? Because the force gets broken down into components. Okay, now for your bell work question, I'm going to ask you, what is the normal force? All right, now to find the normal force, what you want to do is you want to think about FGY, or sorry, sigma Fy. And remember that sigma Fy equals 0, which equals the normal force minus FGY, right? So use the information above. Let's see. Use the information above like this right here, right? Use that and solve for f of n. Everything you need is here. Okay. Now, let's add friction. Let's have that same 24 kilogram equals m, 53 degrees equals theta. Oops, my bad, guys. And let's also say that we don't know the coefficient of friction. Mu equals question mark. If the block is accelerating down the ramp at 0.8 meters per second squared, what is mu? All right, now it seems like a complicated problem. Let's break it down together. We need to find mu. What's our first step? We do the breakdown of the directionality. So let's say that this is x positive and this is y positive, right? Then what do? We draw a free body diagram. Oops. All right. Now the forces, we have the force of gravity, normal force, but this time we have friction, right? So we have a frictional force. Remember, this is kinetic friction. The box is moving down the ramp. So because it's moving down the ramp, you know that friction has to oppose that motion, which means that the force of friction goes up the ramp. Now, Fg can be broken down into components, Fgx and Fgy. So if we do the third step, which is to find sigma Fx and sigma Fy, what are the forces in the x direction? Well, we have Fgx minus the force of friction. What about in the y direction? We have Fgy, no, that's my bad. We have f of n minus Fgy. Between these, we know this one is ma and this one is equal to 0 because the box is accelerating down the ramp. So we also know that we can solve for the FGY and FGX numerically because we know that this is theta. So FGY is equal to FG cosine theta. And we also know that FGX is equal to FG sine theta. All right. Now, if we do this, we can solve for this because we know that FG sigma Fx is equal to FGX, which is equal to Fg sine theta minus the force of friction. Now, do we know the force of friction's equation? Well, if you recall it from last time, the force of friction is equal to mu times the normal force, Fn. So let's rewrite this. F of n times mu equals ma. If we're going to solve for mu, we need to know what f of n is, right? Luckily, we have a second equation, sigma fy. That is equal to f of n minus fgy. Fgy is just fg cosine theta, right? So let me, just go to that. Let me rewrite this. Fgy. All right. So this is equal to f of n minus fg cosine theta, which is all equal to 0. So now if we solve for f of n, we know that f of n is equal to fg cosine theta. So let's take this equation right here and substitute it into f of n in that one. So now putting it all together, we have ma equals fg sine theta minus fg cosine theta times mu, right? This is a minus sign. So now we just do some simple math, and we find that fg cosine theta is equal to fg sine theta minus ma. Oh, I forgot to multiply the mu here. And so mu is equal to fg sine theta minus ma divided by fg cosine theta. Now, if you don't see what I did from here down all the way to here, it was just some algebra. I moved this to the other side. I subtracted by ma, so as you can see in this one. And then I divided both sides by fg cosine theta. Right? And we know that fg is equal to ma or mg. So it's going to be 24 kilograms times 10 meters per second squared. And we know that sine of theta is equal to 0.6. So, no, 0.8, my bad. So sine of 53 is 0.8 minus 24 kilograms times acceleration. The acceleration was stated to be 0.8 meters per second squared. 0.8 meters per second squared. Divide that entire thing by mg cosine of theta, which is 0.6, right? Now, if you run all that math, we get a number 8 minus divided by 248 times 6. We get a number that is mu equals 0.965. And 0.965 is a extremely high coefficient of friction. Right? The closer it is to 1, the more rough it is. So I would say that this is an extremely rough surface. Okay, so that may have taken a lot, but the key takeaway here is that practice makes everything. So I'm going to assign you guys a homework now that I feel more okay with giving you guys problems like this regarding a ramp. And I want you guys to try to do that by the end of the week, all right, before your pre-lab. And I guess we will have a great time learning more about Atwood machines and things like that, all right? So have a wonderful day, everybody.